Welcome, everyone. Today's prep should be short. I just want to do one more example for these limits at infinity when our function is a rational function. So polynomial divided by a polynomial. So our function here is 4x squared minus 3x plus 1, and we're dividing that by 6 plus 4x squared minus 2x cubed, and we're doing the limit as x approaches minus infinity. So what we're doing is we're letting our inputs, x, get very large negative here. And we want to see, well, what happens to our function? And the issue here is infinity is not a number that we can just kind of plug in. So infinity, you want to think of it more as like a place we're going to. It's like a destination. It's not a number that we can just do regular arithmetic with. So we need to convert this expression ultimately into numbers that we can actually kind of do something with. And what we looked at last time is we have that special x to the power n method. So that's what we're going to do. So this is going to ultimately allow us to kind of do the arithmetic so that we can figure out where we're going here. All right, so how did this method work? Well, we look in the denominator and we pick out the largest power of x there. So in this case, it's x cubed. So you kind of just scan through, things might be ordered a little bit differently. So you kind of just scan through the denominator and see we got an x cubed there. So once we've decided on that, then we're going to essentially multiply the numerator and multiply the denominator by a fancy 1. So we're going to multiply this by 1 over x cubed divided by 1 over x cubed. And how that would actually look if we do the distribution, if we distribute that, we'll have our limit sign. And when we take this fraction and we distribute it to each term here, really it's like we're dividing each of those terms by x cubed. So you can think of it either way. We're just going to divide each of these by x cubed. And then we'll do the same thing in the denominator. So if we distribute this, we're going to distribute to each of those, and it's like we're dividing each of them by x cubed. All right, so we've got our expression. Now we want to simplify each of these fractions down as much as they can. Some of them are going to simplify, some of them aren't. And all of the ones that have an x on the top and the x on the bottom, we're going to simplify those down. All right, so let's see how that looks. So that first fraction, the 4x squared over x cubed, that's going to simplify to just 4 over x. Then we have minus. The next fraction, that's going to simplify to just 3 over x squared. And then the last fraction there just kind of stays as is. Then we're dividing. And then 6 over x cubed is fine. And then we got 4 over x. And then minus 2. All right. And notice, as we're kind of going through here, we started with a limit sign. We still are putting a limit sign in each step. Because all we're doing right now is we're working with the function. We haven't actually figured out where we're going yet. So the limit sign has to stay there. All right, so now we can think about, once we get these fractions, the difference between our original function is each of these terms was, as x was going to minus infinity, each of these terms is either going to plus or minus infinity. So, and we can't really do like infinity minus infinity, or it doesn't work that way. But now, since x is going to minus infinity, each of these fractions goes to 0. So this fraction is going to go to 0. Let me get it bigger. Yeah. This fraction is going to go to 0. This one's going to go to 0. This one's going to go to 0. That one's going to go to 0. So all these little fractions are going to 0. The only thing we're going to have left is that 2. So now we can actually say what this limit is doing. So that first fraction goes to 0. Then we have minus 0, then plus 0, then 0 plus 0 minus 2. All right. And if we simplify that, we end up with 0 over negative 2. And I picked this one because this is a common mistake. We kind of get into the habit. We've been doing limits now, and we've seen things like 0 over 0 or c over 0. So we're kind of trained at this point to be a little fearful of 0 here in a fraction. So it's worth noting here. Note. What do we want to note? 0 over c is okay. So if we have 0 divided by a constant that's not 0, that's just 0. So the only ones that give us issues are the 0 over 0 or the c over 0. So those are the ones that give us issues. We know 0 over 0, that's a whole different game. C over 0, if that's our limit, then it's either plus or minus infinity. But 0 over c, perfectly good perfectly good number. So 0 over negative 2 is perfectly fine. So this limit goes to 0, ultimately. All right, so this is the idea with these limits at infinity for rational functions. We're using this x to the n method. And we really are multiplying by a fancy 1, distribute it to each of the individual terms. So it's like we're dividing each of those terms by the largest power that we picked out. Simplify each of the fractions down. So this is an important step. I want to see the fractions all simplified as much as they can. And then once we get those fractions simplified, then we can actually say where each of those individual terms is going. And the fractions all go to 0. And that's because, pop back up here, of this 1 over x to the n. So this is what we looked at. So each of those terms goes to 0. All right, and it doesn't matter if x is going to minus infinity or plus infinity. 1 over x to the n goes to 0 in either direction. All right, so that's it for today. So we're going to definitely be practicing more of this and kind of looking at other types of functions as well in class. So we'll see you then. Bye-bye.